Hi, guys. By now, you've completed your circular motion lab, and you're probably watching this video to get a little help on how you can finish analyzing the data. So remember, this was two parts. We are trying to figure out the relationship between, in part one, the centripetal force, or the tension in the string, and the velocity of the stopper as it's going around. So if we're trying to figure out how these two variables are related, we are keeping the other two variables, a grand total of 4, constant. So I'm using some data that we collected today. And you would obviously be using your own data. So in this first part, we're looking at the relationship between the centripetal force, which is created by that downward pull of your washers. And so we took the mass of the washers and multiplied by G. M times G gives us the weight of the washers, which is then equal to the tension force in the string, which is then equal to that centripetal force. The same tension in the string is what's keeping that mass, that stopper, moving around in a circle. So we just took this and multiplied by 9.81 to get the forces. So we're going to plot the forces versus the velocities that we got. So you can see the velocities. In this case, we went from, I think we had 15 washers down to 10, down to 5 maybe. And then we decided to go back up to a larger number of washers.
Physical education, come on down.
Thanks, Mr. Bunicor. And so you can see the numbers go down, but then they go back up again. We decided to go back and add some more washers. So in here, these periods, remember, were the amount of time that it takes for the stopper to go around. So in this case, it was 9 seconds for 15 revolutions. So I divided to get that. And then we had similar calculations here. So back to what I was saying originally, we want to look at the relationship between the centripetal force here, and how fast that rubber stopper is going around, the velocity. We calculated the velocities using 2 pi r over t, which is basically saying distance, circumference, distance, divided by the time, which is the period it took for it to go around once. It took 0.6 seconds to go around once here, 0.69 seconds to go around once here. That is the time it takes for one revolution, which is the period t. So we're going to plot centripetal force versus velocity. Remember, I want to see one sample calculation for just pick one of each. Don't show me all of them, and make sure you include units. So the graph. I'm going to try going back to the graphical analysis graph. I hope that doesn't confuse you by going back and forth. Before we were using a spreadsheet. To be honest, I probably could have put a spreadsheet in here. Maybe should have next time. But I'm going to have you go back to the graphical analysis program. It's certainly a more intuitive program. It's easier for doing curve fit and finding the linear regression or the slope. So I'm going to open that up. Actually, before I do that, though, I already know I'm going to plot the forces. So I'm going to highlight my forces right here. Copy those. I'm going to open up my graphical analysis program, Logger Pro. And I want the force to be I'm going to have it on my y-axis so that my y equals mx plus b matches up with the standard equation better. So I'm going to click on this top box here, hit paste, and you see all those numbers go in there. I'm not sure why it doesn't do the first one, but actually, since this guy was kind of out of order, I'm going to cut that and put it up here. Since it was they got smaller and then up again, I'm going to put that guy up here so everything's in nice order anyhow. And remember what those were. So I just double clicked on my Y up here. Please do this. Double click on the Y. This little column option thing pops up. And this is where you're going to put your labels in. So this is our velocity. So type that in as velocity. Don't put units in there. There's a short name, which you can just use like the symbol for that. So a little V. And the units here are actually going to be meters per second. The radian, or the circumference is in meters, and the periods in seconds. So I'll hit done on that. So that way I remember these are velocities. You know what I just realized? I think those are forces. I decided to do the forces first, didn't I? So I selected, where are those guys? Those are forces. That's easy to fix. Good enough. So now I'm going to, maybe I should fix those first. So I want those to be on my forces. I want to be on my y-axis. So I'm good. I just messed up on the labeling, that's all. Force, capital F, units, newtons. Okay. All right, so those are my forces in newtons. Let's go back to my data table. I want my velocities, so I'm going to highlight all of my velocities here. Again, remember this last guy, so copy. This last guy is kind of the out of order one. Back to my graphical analysis, put it in the first box, hit V, and it leaves that blank, but that's cool. I'm going to put that X up on top. You could just cut and paste the whole column and shift it up if you didn't have this problem. Paste. All right, so that 6 went with the 1.03. Double click on this guy. What was this? These are my velocities. Okay, same problem typing that. Velocity. Put V in there. I'll put meters per second here. All right, I'm good. Hit done. So now I've properly labeled these. Those labels automatically appear on my graph. You can see the data points down here. I have one that's a little suspect, but I kind of wish this would fill the page a little bit. So we have some scaling issues here. The easiest way to hit to change or get to the scaling, you can go up to options, but if you just kind of double click on, just put your cursor near the scale and double click on it, graph options show up, which is under options. You want to put a title of your graph. I'm going to skip that for now and hit axes options. And much better than the sheets one, but still a little bit confusing the first time you see it. The label for y-axis is already taken care of. We have that as, I don't know why that's not on there, to be honest. Force. It says force right there. What I want to do is I want to make, this goes from 0 to about 1. So right now it's doing 0 to 10. So I'm going to hit this little scaling option here. And I'm going to choose manual. I'm going to say, yeah, let's go up to like 2. 0 to 2, because this goes from 0 to 1. And so there's all the y stuff. Kind of strangely, the x is down here. So x-axis, velocity, right? Same thing. They're going from 0 to 10. But if you look at our velocities, the highest velocity we have is 6. It's actually not bad. We could use that. I mean, I don't know. Let's make this 7 so it fills a little bit more. If I hit done now, you can see this is much bigger. Fills the page a lot better. I could have even gone like 1.5, I guess, for this. That might have made more sense. So that's easy to do. I'll just click this, go back, do this like 1.5, 1.5. Go up a little bit higher here. I'm going to leave my 0, 0 origin. I know I could have shifted this to the left. So here I have my force versus my velocity. And this actually looks kind of linear, right? You can select all that data. If you don't select it, it'll automatically pick all of it. When I choose R up here, see this right up here? R, that's regression line. This is automatically, boom, takes a slope, calculates the slope for you right there, 0.2590, gives you the y-intercept, gives you that kind of R squared on the other program, which is the correlation coefficient. The closer this is to 1, the more linear this is. I don't know, I'd probably stop here and say, yeah, these guys look linear. I agree, they kind of do. Unfortunately, that's not supporting where we're heading here. So look, let's remember, this is 0.9952. It's actually directly proportional to the velocity squared. So let's see if we can get better than 0.9952 with velocity squared. Your data might not be quite as linear looking as mine. So the easiest way to do that is make another column here with velocity squared instead of velocity. So pay attention. I'm going to go up to, not the options, to data. I'm going to choose new calculated column. I'm going to have it do the calculations for me. I don't want to square all those guys and put them in myself. So I'm going to hit new calculated column. It's going to ask me, what do you want to name it? I'm going to call it velocity squared. Caret 2. And we'll say this is V caret 2 for a short name. And we'll say this is meters per second squared caret 2. Squared. Okay. And then down here, I have to tell it to do that math. So this expression thing is where you do the math. It's kind of like the spreadsheet. Except what you're going to do is say, all right, what do I want to do? I want to square the velocities. The velocities, that's one of my columns. That's one of my variables. So I'm going to click on the variables and say, yeah, go get the velocities. So it's going to go get my velocities. And then I'm going to do caret 2. say square them all, please. And I'll hit done. And you'll notice back up here in my data table, I get a new column that says velocity. I'm going to make my graph a little smaller. Maybe we can pull this over so you can see what's going on over here. Slide over here. There's 3 columns up there: velocity, force, and velocity squared, right? 6 squared, 36, and so on. So let's back up. Remember, I made this graph of force versus velocity, and it looks, within reason as if it's linear. So 0.9952. Let me get rid of this. And I'm going to see what force and velocity squared gives me. I kind of wish this was a little more curved. Actually, I think this last point is a little funny, and these guys kind of have a nice gradual curve to them. But I'm going to click down here where it says velocity. So I just clicked right on the word velocity. And it's saying, what do you want to graph down here on this x-axis? Do you want to leave velocity? You want to put force down here? You want to put velocity squared? Because I do have a velocity squared column now. So I'm going to say, no, let's replace velocity with velocity squared. So I select that and see the velocity squared. Again, this point, I think these 4 are nice linear, but let's hit regression line on this. I'll go back up where the big R is under the graph. I click on that and it draws a line through my data points. And 0.99, remember it was like 0.9956, I think? This is a little bit closer to 1. So this is a little bit more linear. If I got rid of that point, I think it would be even better. I worry that my really slow one was kind of not good data. I can. That's my really slow one down here. I could click on this little 5 over here and delete that point. See, it's gone. It was right here. And just kind of for kicks, hit regression line on this. Yeah, a little bit better, 0.9988. This does look a little bit more linear. All right. Leave yours. It's okay. But unless you have one that's clearly out of whack, then get rid of it. So this is my first graph. I want force versus velocity squared. I need this slope. You can move this guy around. I need this slope, all right, 0.02693. Like right now, I'm just going to write that down, 0.02693. I don't really need that many significant figures. 0.027 is fine. I don't really need my y-intercept for this. So this is y equals mx plus b. Don't forget, y equals mx plus b. Y is force. So we have an equation here that says force equals the slope, 0.026 or 27, times the velocity squared. Okay? So that's the equation we're trying to create. If this is truly linear, then it looks like force is directly proportional to the velocity squared. All right. So when you go back to our lab, number 2 says, show the mathematical relationship between force and v to some power. You must determine the value of x. That's what I just did. It wasn't, albeit it wasn't convincing, I agree, given the data that I had, that this x is a 2, that it's squared versus 1. I mean, the correlation, being equal to 1 was certainly better when this was a 2 than when it was a 1. All right, but I understand how initially you would look at the first one and say, yeah, that looks pretty linear, and might go with that. But it's definitely better when we square the velocities. And we could try other power functions, and hopefully you would all agree that the squaring is the best one to make the relationship linear. All right, so I'm asking you to show the mathematical relationship between these things, including the slope as shown by your graph. And that's basically what I just said to you a minute ago. I said, well, the centripetal force, I don't know what that underlined thing is doing there. Centripetal force equals, there's some slope, which we said was 0.02693. You could put units in there. What are the units for my slope? All right, I'm going to leave that. You got to make sure you get those in there. Some units. I'm just kind of putting that in there as a placeholder. So this is y equals m. Where's x? All right, well, so it's going to be times. I don't know what just happened there. So times x. What's your x-axis? Well, it's v squared. Okay. This is in Sheets. I would know how to do this in Word in a second, but let's just do caret 2. Okay, so y equals m times x. And you could put your y-intercept in there too, plus whatever b is. All right, that's our mathematical relationship showing FC, put a little c on it, and v to the second. Now it says, look at your graph. It should be obvious that the slope is constant. Yes, it was. What possible variables were kept constant in this portion of the lab? Well, if you go back to our notes, which if I was smart, I would have had those open. You know what I would do a really fast Google search. I bet this will work. Centripetal force equation. There it is, boom. So FC equals mv squared over r. That is where we're trying to go. We're trying to verify this, trying to prove this. So is the centripetal force directly proportional to the velocity squared? Our graph indicates that. And we have a constant slope. Well, could this be y equals mx plus b in disguise? Y equals, don't confuse this m with our slope. We have a slope, a value for the slope, and then this is x. So m over r could be the slope, right? Y equals m times x. M over r is the slope. M over r is the slope. What does suggest the meaning of the slope in terms of constants? M over r is the slope. The slope equals m over r. Are these guys, slope is constant. Was the mass of the stopper the same the whole time? Yes. Was the radius the same? Yeah, this is the one where we kept the radius the same. So what is the mass of your stopper? 0.0124. What is the radius? 0.47, all the way across. What is 0.0124 divided by 0.47 equal to? Is it close to the value of 0.0269 that we got for the slope? Check it out. And you're going to have your own numbers to play with. You might actually get the units from up here, from right here. What are the units for the mass? What are the units for the radius? Those are your units right here. Okay. Now we're basically going to repeat that same process in part 2. But now instead of the force versus the velocity, we're going to do the velocity versus the radius. And if you go back to our little equation here, we're looking at these two, the velocity and the radius. So what's going to be held constant? The mass of the stopper, that's always constant. And we're going to keep the force the same. So we're not going to change the number of washers hanging off the end, which creates a centripetal force. So we want to see, we got to kind of rearrange this to make it be y. One of these could be y. One of these is y, one of them is x. And then what's your slope going to be? Something constant that has to do with these two. So I'm not going to do that one for you, but it's the same process. All right, and you have that equation to kind of go back to and check the algebra on. But again, notice, what do we keep the same? The mass of the stopper. And in this case, we kept the mass of washers, which is the force constant. So 0.0124, I don't know, times 0.68, maybe 0.68 divided by 0.0124. I don't know. Some combination of those guys is my slope. And that's what I'm looking for in those same two questions. You know, what do we keep constant? I just answered that for you. What's the meaning of the slope? I don't know. It's like I said, it's either the force divided by the mass, or it's the mass divided by the force times the mass. I don't know. You have to figure that out by comparing it to your slope. You can actually figure it out by looking at this equation. Okay? So new graph, whole new graph with v squared in r on that. And so just take your v squared data and your r data and make a graph. What did I do with it? There it is. All right. Again, you could just type in your, you could try making two graphs for that too. I'm saying here you have to figure out whether this should be V. That's what I meant, So try R and V, plot them. And then try R and V squared, plot it. Hopefully it's more linear with V squared. I'm telling you it should be. All right, so hopefully, if you got a little confused there, you can pause it, replay it, but hopefully that will help you to figure out how to get to the analysis portion of this particular lab. If you're really comfortable with Google Sheets graphing program and you can get to the slope and you remember how to do that exactly as we did before, I'm fine with you using that. I just would like to make sure you use some kind of graphing program to have it calculate that slope for you. Certainly easier to manipulate data once you have the graph. You don't have to regraph like I did. I decided to get rid of one data point. All right. Don't forget, if you do use this program, this is the one we had trouble with when you go to share it with me. You just can't share it in this file. You have to download it and save it and then share it to me. Or you might just want to do a screenshot if that's easier. But don't share it right out of this file. All right, so I'm going to sign off here. If you have any questions, let me know. And I hope that helps.